and the base put in there. So just if you like it better, this says f of x equals log base b of x. This is the same thing as y equals. It's just that notation from the functions unit. But if you would prefer y equals, it's the same thing. And this is the general shape if this little subscript, your little base, is bigger than 1. So this would not be the shape if our subscript was like a half or something like that. But this is just the subscript if it's like 2, 4, 6, 8, whatever the subscript for the log. So just in general. Okay, now, in general, just like our exponential functions, the log functions have an asymptote, but for the log functions, the asymptote is actually vertical. So if you don't have any shifting or anything like that, which I don't in that little example there, the asymptote is the y-axis, which the y-axis, and I know this is weird, but it has the equation x equals 0. So all the x coordinates up and down the y-axis are the same. They're all 0. And so that would be your asymptote, where your graph is going to get really close to that, but never touch it, never go over it. Now, just in general, I'm going to write this here so you guys can see it on the graph. The domain for any log function is going to be your asymptote, which for this general, it's not shifted or anything, but it'll be the asymptote, and then it goes to the right forever, so it'll go to infinity. That would be your general domain. And your range for all these logs that we're going to graph today, it goes, like this piece goes down forever. And then I know this looks like it kind of levels off, but it does go up forever. So the range for every single one of these logs that we're going to graph, no matter where the asymptote's at, is going to be negative infinity to infinity. Now the domain might change a little bit based on the asymptote. If it's shifted, we're going to do that more on the back side of this note paper. Okay, now let me give you a little concrete example over here. This has log base 5 of x. This would be the same thing as y equals the log base 5 of x. Okay, now majority of the points on this graph are super weird numbers, but they would all have a couple of nice points. And if you see the graph over here, just in general, this will always have the point, if it's not shifted, 1, 0, and then whatever the little subscript is. So for this general case, they use the subscript of b and then 1. So what you guys see on my actual graph over here that has a subscript put in is that it has the point 1, 0, and it has the point 5, 1. So let me just show you why that works here real quick. So if I do, let me just plug these points in, I'll show you why it works. So if I do y equals log base 5, and I plug in 1 for x, just to show you why this works. I'm going to convert this to an exponential just real quick to get rid of the logarithm. I would have 5 to the y equals 1. What would y have to be to make that true? Anything to this power is 1. 0. Okay, so that's why when I plug in 1, y has to be 0 there. That's why you're going to always have that point 1, 0 whenever you have a log function that's not shifted. If it's shifted, we're going to manipulate that a little bit. Okay, similar argument. If I plug in the little subscript for the base, for my graph here I've got 5. If I do y equals log base 5 of 5, and I just convert that to an exponential real quick, I'm just trying to show you where they get these points from. I'm going to push that y up in the air, and this would say 5 to the y equals 5 to get rid of that logarithm. And if I look at that, I know it's not written here, but if I just have a plain 5 by itself, it's to the first power. So to make that lovely little statement true, y would have to be 1. So that's going to correspond to the point on the graph. I plugged in 5 for x, and the exponent for y has to be 1 to make that true. So that's where you're going to get that point. So every log function, not shifted, as the point 1, 0, and then whatever the lovely little subscript is, 1. Does anybody have a question? Okay, there's kind of two ways to graph these logarithms because, like I said, most of the points on this graph are like super weird decimals. So one way to do it is actually to graph its inverse. So this says log functions, right? And exponential functions, we were doing that last week, are inverses of each other. So I'm going to show you this here real quick. And then to graph the log, what you can actually do is find the inverse. Okay, now a lot of people were not super familiar with this last period, so I don't know if you guys didn't do this first semester or not, so I'm just going to go over this. If you're finding an inverse, we're going to graph the log base 3, and I'm just going to use this space over here. If I want to find the inverse of any function, this will be just literally one step. If you ever want to find an inverse, this is what it says: switch x and y and solve for y. So I'm going to graph y equals log base 3 of x by graphing the inverse first. To find the inverse, you're just going to switch x and y. So I'm going to write x equals log base 3 of y. And then to actually write the equation of the inverse, you want y by itself. That's why it says solve for y. Just to get rid of the log, I'm just going to switch this to an exponential real quick. So that base of the log becomes base of my exponent, and that would tell you 3 to the x equals y. So that is the inverse of the log base 3 of x. And if you guys look down here underneath, I've already got this kind of set up for us here. So these two, these are inverses of each other. Exponential and the log are inverses of each other. All right, so we did a bunch of exponential graphs. I had you guys just like look up the table on your graphing calculator. You could do that here. Just going to graph y equals 3 to the x real quick. I'm just going to do it by hand, but if you want to use your graphing calculator to make a table, you could totally do that. So if I just plug in, I did -2, -1, 0, 1, 2. This would be 3 to the -2 power, which would be 1 over 3 squared. You don't have to write all that out, but this would be 1/9, which I'm going to kind of estimate on the graph because it's not going to be a nice number. If I plug in -1 to 3 to the x, 3 to the -1, which would be 1 over 3, so just 1/3. 3 to the 0, anything to the 0 power is 1. 3 to the first would just be 3, and then 3 squared would be 9. So I'm just plugging in x values that I had in the table already ready for us. And you could do that on your graphing calculator, or you can do it by hand like I just did there. To graph the inverse then, you know how I switched x and y in the equation? I'm going to just do that with the table. All right, so with the table, if you have your x and y coordinates switched, that'll give you the inverse. So that first point was -2, 1/9. On the inverse, it would be 1/9 -2. On the original, -1, 1/3. On the inverse, you just switch x and y, so it'd be 1/3 -1. And I'm just going to switch each one of these. The x coordinate becomes the y coordinate, and the y coordinate becomes the x coordinate whenever you have inverses. So that's with the table. They're literally just flipped over. And I'm going to put these two on the graph so you can see graphically how this looks. So the exponential, I know you guys know this already, but the exponential is just y equals 3 to the x. So the asymptote there is going to be the x-axis. So I'm just going to graph this in the same color as my table. Now, -2, 1/9 is not a nice point, so just kind of do your best to kind of estimate where that would be. And then -1, 1/3, again, just kind of estimate a little bit higher up than the point you just did. The rest of these will be nice points. So 0, 1, 1, 3, 2, 9. Those are all nice points. Okay, now this makes that kind of like a J shape here. We're going to get real close to the x-axis, but we're not going to touch it and we're not going to go over it. So something like that. And you guys, sorry, I think I made this graph a little too big. Okay, now just for what I just graphed, the domain. So this is a little review. Domain for any exponential. This goes left, it goes up really fast, but it goes left and right forever. So the domain for any exponential function, -infinity to infinity. Sorry if that's kind of small. I'm just trying to do it so you guys can see the graph. Okay, now the range, right? I don't start touching any part of that graph until I hop over the x-axis. So the range, and we don't use a bracket, we use parentheses because you don't actually touch the x-axis. So 0 to infinity. All those y values are positive. And then the asymptote for that exponential, I kind of highlighted it, is the x-axis, which has the equation y equals 0. Any exponential function has the asymptote is a horizontal line, so it's a flat line. Now, when we do a log, it's the inverse of that, so it's literally going to flip it over. It flips it over this little dotted line that I have here. This is the line, let me grab a little marker here. this little dotted line is y equals x. Anytime you have inverses of each other, they are reflection over the line y equals x. That's why I put that little dotted line so you can see that. So I'm going to graph this log here in a second. If you fold your paper in half on that diagonal line, the two functions would match up. They're a reflection of each other over that line. So when you graph this, it's a little tricky. So my x coordinate is 1/9. So here, I'll make it a little bit bigger. Hopefully you guys can see it better. So just like just go over just a little bit, I would say, from the origin, and then I'm going to go down to -2. The next point, the x value is 1/3. So again, just do your best, just kind of estimate, go a little bit farther over than what you just did, and go down to -1. And then every log function that's not shifted has the point 1, 0, so that'll be a nice point. Over 3 up 1, that's a nice point. And then over 9 up 2, that's also a nice point. So just the ones really close to the x-axis are kind of rough to graph because they're fractions and you just kind of have to estimate. In this case, what I'm doing is I'm going to get really close to the y-axis, but never touch it, never go over it. So when I do the asymptote here, it's actually a vertical line. So just get kind of really close to the y-axis, and then we're just going to kind of do a general shape there. So it should be, and hopefully if I did a decent job there, hopefully you guys can see, if I did fold the graph in half on that little dotted line, it would match up on either side. And so the domain here, sorry, so you can see the whole graph. Okay, now, the lovely little blue graph on my paper, I don't touch any part of that graph till I hop over the y-axis. So the domain here actually, again, I don't touch the asymptote, so I have a parenthesis, not a bracket. So 0, and then it goes to the right forever. So 0 to infinity. And then your range, I know this looks like it levels out, but this does go down forever, and then this does gradually go up forever. So the range is going to be -infinity to infinity. And the asymptote for that is actually a vertical line, x equals 0. So anytime you have a log function, it's going to have a vertical asymptote. And then maybe just real quick before you guys flip over, I just wanted to show you this. So at the very bottom here, if you do have inverses of each other, the domain of the original will be the range of the inverse. They switch. Anytime you have inverses, it doesn't have to just be logs and exponentials. It could be like square roots and quadratics. It could be cube roots and cubics. Like anytime you do this, the domain of the original is the range of the inverse. And then same thing, the range of the inverse is, or range of the original is the domain of the inverse. So even if I didn't have a graph or an equation or something like that, I could tell you the domain and range if I had it for the original, what it would be for the inverse just by switching them. Okay, now the rest of what we're doing today is going to be shifting, and I'm just going to look for a general shape, and I'm going to look for 2 points. All right, so in general, if you don't have a shift, this just says log base b of x. This would be like your parent function. No shifting has taken place. Always has the point 1, 0, and then whatever the subscript is, 1. All right, now if it's shifted, we would alter those points, and the shifting works just like all the other shifting we've talked about. So inside the log with the x here, this says x minus h. It's going to be the opposite of what it looks like, and that's going to shift your graph left or right. Outside, not taking the log of it, is plus or minus something out here. I got plus k. You're just going to copy that value, and that's going to tell you how the graph would shift up or down if it's there. So inside with the x, left or right. Outside, not in the parentheses, is going to shift the graph up or down. So way you think goes with the outside, the opposite of what it looks like goes with the inside. So what I did was I graphed the same graph that's on the front, the log base 5 of x. We're going to shift this graph based on the function that's written right above here. So log base 5, x minus 3. So if I have x minus 3, what would that do to the graph? How would it move it? To the right. Okay, it looks like a minus 3, it's really plus 3. So this is going to go right 3. Now, what I'm going to do is I'm going to add 3 to my x-coordinate. I'm going to do that in a second, but that's what I'm going to do. Okay, what is the plus 1 going to do? How is that going to shift the graph? Up 1, right? Okay, so up 1, right? So I'm going to add 1 to my y-coordinate. That's what I'm going to do. All right, so those 2 points that we have, right? We have the point, let's see. I'm going to go right through. I'm just going to try and put this into place so I'm not on top of the graph here. Okay, so my original point, I'm going to pick a color here. My original point, I have 1, 0, and then I have 5, 1. That is on the unshifted graph. Okay, now I'm going to shift the graph. So what I'm going to do for each one of those points, I'm going to add 3 to the x-coordinate because I'm going to go 3 to the right, and I'm moving it up 1. That's going to affect the y-coordinate, and I'm going to add 1 to the y-coordinate. All right, so my 2 new points then, I'm going to scooch this up a little bit. This would be, okay, I'm not going to write it there because that's going to run into the next graph. So if I add 1 to 3, this would end up being 4, 1 would be the new point, and 5, 1, if I add 3, that would be 8, and if I add 1 to 1, that would be 2. So I'm adding 3 to that x-coordinate, adding 1 to the y-coordinate to get that shift going. Same thing with that other point. I'm going to add 3 to the x-coordinate, so 5 and 3 is 8. Add 1 to the y-coordinate, 1 and 2 is going to be me, or sorry, 1 and 1 is going to give me 2. Okay, now I'm just going to plot these 2 points, and sorry, there's no grid mark on here, so just kind of do your best to kind of eyeball like 4, 1 and 8, 2 is going to be up here. Can anybody tell me what the asymptote for the shifted graph should be? That's for this original one.
Oh.
If I go to the right 3, how's that going to affect the asymptote? Does that make sense? Okay, so I'm moving everything. So original graph is at x equals 0. If I go to the right 3, then that is actually going to be my asymptote. So I'm just going to draw a little vertical line right in there. That'll be my asymptote. And then just take those 2 points. You're just going to get kind of close to that. Don't touch it. Don't go over it. And then that general shape through those 2 points. Should look something like that. So what's on the graph already, that's no shifting of the y equals log base 5 of x. We're moving it over 3 and up 1, and that's where we're going to shift it to. Okay, now your domain for any of these graphs should just be whatever your asymptote is. That we're going right 3, so my asymptote's 3. So I don't start touching this graph until I hop over that 3, and then it does go to the right forever. And then I promise every single one of these graphs for the logs range is negative infinity to infinity. It does go up and down forever. As it goes up, it just goes up really slowly. And then we put the asymptote on the graph right there. Should just be x equals 3. Okay, is anybody having a question at the moment? Okay, now, if I give you, this is just the parent function on the graph. If I give you log base 5, x plus 2 minus 4. Can anybody just raise your hand and tell me, like, how would that shift the graph? So if I do x plus 2, I got that in parentheses, and then minus 4. What do you think? Perfect. Okay, so this is going to be left 2, down 4, right? Okay. Now, I'm going to just scooch this up just a little bit. So those 2 points that we were talking about, right? We had 1, 0 and 5, 1 in the original graph. So if I'm going to change these to do that shift, left 2, you're going to subtract 2 from the x-coordinate, and then you're going to subtract 4 from the y-coordinate. So left 2, we're just going to affect the x-coordinate, left or right. Up or down affects the y-coordinate. So if I take and start with 1, if I subtract 2, be negative 1, 0 minus 4 would be negative 4. So that's that shifted point. If I take 5, 1, then I'm going to subtract 2, that would be 3. 1 minus 4 for the y-coordinate would be negative 3. So that's that point shifted to the left 3 and then down 4. Now, what should my asymptote be for my shifted graph? X equals what?
2.
Negative 2, there you go. Okay, so we're going to have a nice vertexal line at x equals -2. So if I just come over to the graph, I'm just going to do that real quick here. Here's -2. And then I'm just going to plot the 2 points I just shifted, all right? So I've got the point -1, -4, so it's kind of down here a little bit. And then I've got the point 3, -3. And I'm just going to do kind of a general shape here. So we're going to get close to that asymptote, but not touch it, not go over it. That's shifting that original graph. We're going left 2 and down 4. Now, your domain for that shifted graph, it should just start right after you hop over your asymptote. So it should be -2, but not a bracket because you don't touch it. And then it goes to the right forever. And then range for all of these should be up and down forever, -infinity to infinity. Or if you guys prefer, I don't care if you want to write that symbol for all real numbers. If you don't want to write the interval, that's fine. But it's only going to go for the range for your logs. It's not going to go for the domain. You're going to have to kind of look at the graph to figure that out. Is anybody having a question? Okay. Now, I'm going to have you guys just practice this a little bit more, but this is log base 4 instead of log base 5. All right, so just in general, every single one of these, if I didn't shift it, if I had a log base 4, I would have the 0.10, and then since I switched up my subscript here, the other point would be 4,1. So I'm going to shift those 2 points for each of these graphs. So if I give you, excuse me, log base 4, and then in parentheses, I have x minus 4. Who could just raise your hand and tell me, how would that -4, like log base 4, x minus 4, what would that do to the graph? How would that move it? Yeah. So do you remember what I was doing here on the front? Let me switch this back. Every log function, I tried to, this is where I was doing that exponential. So if I just switch this up and I put a 4 here, log base 4, this would be 4 to the y equals 1. Every single time that y value, if it's going to be equal to 1, it has to be 0. And if I switched the 5 up here, so this would be like a 4 and 4 instead of 5 and 5, it has to be 1. So every time it's whatever the little subscript is and 1, and then 1, 0. If you wanted to actually like plug it in, you could do that. So here, I'll just do it real quick. So if I actually did the log base 4 and I plugged in 1, right? To get rid of the log, I'd swing this, and I had to have 4 to the y equals 1. In that case, y has to be 0 to make that true. So that would be that point. I plugged in 1, and I got 0. So that's that 1, 0. That's where it's coming from. If you did the same thing, if I did y equals log base 4 of 4, if I convert that to an exponential real quick, I would get rid of the log, swing the 4. You'd have 4 to the y equals 4. The only way for that to be true would be if y was equal to 1, because you have 4 to the y, and then just 4 would be the exponent. So if I plug in 4, then I get 1 as my x. But you could, you could literally do this with any log. If I change that up to be like base 10, it would be 1, 0, and 10, 1. If I change the base to be like log base, 24, it would be 1, 0, and then 24, 1. It would always work. The rest of the points are usually just kind of gross decimals, so those are the easiest ones to plug in to get actual points on the graph. Really good question. But that's where those points come from that original, if you were to actually convert it to an exponential real quick. Okay, so for this guy, I'm going to move the opposite way, I think. So this says -4, so this is going to actually move to the right 4. Now, there's no shift up or down here. So what I would do for this graph is I would just add 4 to the x coordinate. So I'm going to take those 2 points. I've got the 1, 0 and the 4, 1. All you're going to do, we're going to shift this right 4. The y coordinate is going to stay the same, and we're just going to add 4 to the x coordinate. So 1, 0 is going to become, if I add 4, 5, 0. And 4, 1 is going to become 8, 1. There's no shift up or down. So I'm just taking those 2 points. If we're going to the right 4, we're just going to add 4 to the x. Left and right, you're going to affect the x. Up and down, you're going to affect the y. Okay, now that 4 is going to affect your asymptote. So I'm going to draw whatever it is, as I'm adding 4, I'm going to have a vertical line at 4. So that's x equals 4. And then those 2 points should be on the right side of that if I did that correctly. So 5, 0 would be right here, 8, 1 right here, and then we're just going to sketch, like just kind of that general shape that you've seen in all these graphs today. Just get kind of close to that asymptote, but don't touch it, don't go over it. I'll just look for those 2 points that you would have shifted. All right, and then I'm going to see if I can scooch this up just a little bit to do the domain, range, and asymptote. Okay, so your domain should be your asymptote, which is 4 to infinity, and your range for every single one of these, up and down forever, negative infinity to infinity, are all real numbers. And the asymptote I put on the graph there, x is 4. If I look at the one in the middle here, I've got log base 4 of x minus 2. How would that graph shift? Just, whoops, the y equals, oh my goodness, sorry, I just messed something up, guys. How would that shift the graph of y equals log base 4 of x? What would that do? What would the negative 2 do? Down 2, that's it. All right, so this guy's going down 2. So there is no shift left or right here. So all you're going to do is subtract 2, but only from the y coordinate. The x coordinate's not going to be affected. So I'm going to take those 2 original points. You guys see them right there. 1, 0, and 4, 1. So 1, 0, the x value is not moving here. So the 1, 0 is going to stay the same, or the 1's going to stay the same. 0, we're going to subtract 2. So it would go 1, negative 2. The point 4, 1, we're not going to change the x coordinate because we're not shifting left or right. We are going to change the y coordinate because we're shifting down. So I'm going to take 1 minus 2 would make it negative 1. And I'm just going to plot those 2 points real quick. So 1, negative 2, 4, negative 1. Now, because you don't move left or right, your asymptote is actually just x equals 0. It was just a plain x by itself. There was no parentheses or anything. So if that's the case, if you don't move left or right, the asymptote's just going to be x equals 0. So then I'm just going to sketch this, just kind of get close to that, but don't touch it, don't go over it. And then I'm just going to scooch it up just a little tiny bit. Your domain here starts with your asymptote, so it would be 0 to infinity. And then your range, up and down forever, negative infinity to infinity, all real numbers, however you want to write it. Asymptote, vertical line, so it's always x equals a number. I call it vertexal to help me remember it. So it'll be x equals 0. Okay, now the last one, I got 2 shifts going on here, right? So I'm going to go, it's plus 1, so I'm going to go the opposite of what it looks like. So I'm going to go left 1, plus 3, and I'm going to go up 3. Okay, now what I'm going to do to those 2 points, I'm just going to kind of use the margin to the side, is I'm going to subtract 1 from the x coordinate, and I'm going to add 3 to the y coordinate. So the left or right affects the x coordinate, the up or down affects the y coordinate. All right, so my original, pull it down so you guys can see them. Okay, so 1, 0. If I subtract 1, that's going to be 0, and I add 3 to 0, that'll be the point 0, 3. All right, the other point before I shift it is 4, 1. So I'm going to subtract 1 from 4, so that's going to give me 3. And I'm going to add 3 to the 1, so that's going to give me 4. So after I shift, I'm going to go left 1, up 3. The new 2 points then would be 0, 3, and 3, 4. And my asymptote should be at the negative 1, so I'm just going to draw a nice little vertical line at negative 1. We're going to get real close to that, not touch it, not go over it, and I'm just looking for you guys to do, just like I said, that general shape and those 2 points. That's what I would be looking for. Domain for every single one of these, it's just whatever your asymptote is. So for this one, it's negative 1 to infinity, and then my range, negative infinity to infinity, and then, like I said, the asymptote was negative 1, so it's just x equals that x value. So it's a vertical line where all the x coordinates are negative 1. Does anybody have any questions? The homework is really similar to this. So the front side of the homework is kind of like that very first example.